All right, let's go ahead and get started. It looks like everyone's here that is going to be here. All right, so welcome to the Unit Conversion and Dimensional Analysis Fall 2020 workshop. My name is Eric Steffens, and first thing we'll go over is, what is dimensional analysis? Well, it is a powerful technique for handling unit conversion math using things called conversion factors, which we'll go over in a minute. Many formulas throughout the sciences can be evaluated using this technique, including chemistry, physics, and biology. The normal technique is a quantitative technique where you're using both the numbers and the units to solve the problem, but there is also a qualitative technique that allows you to quickly check if a solution is likely to be wrong or not before you go through the whole entering all your numbers into the calculator and everything. Also, if anyone has any questions, feel free to post a message in the chat. I'll be glad to answer any that anyone has. So conversion factors are of critical importance to this technique. They're ratios of some amount in one unit to an equivalent amount in another unit. So conversion factors will essentially evaluate to 1. They don't actually change the value of the number, they just change how it's expressed. And in general, because of this, conversion factors are reversible. If you change which order the ratio is in, it converts the opposite units. A good example of this is that 1 foot equals 12 inches. This will result in a conversion factor that would turn inches into feet. You might write it as 1 foot over 12 inches. If you were to reverse it, you would get that 12 inches equals 1 foot, or 12 inches over 1 foot, or 12 inches per 1 foot. That would convert from feet to inches. An example that you see a lot in chemistry is Avogadro's number, 6.022 times 10 to the 23rd. That's the number of molecules in 1 mole of a substance. A third example is that if a certain model of car gets 30 miles per gallon, you can use that as a conversion factor to turn the number of gallons of gasoline burnt into miles traveled, or vice versa. So in this example, this is a conversion factor that's specific to a particular object or situation rather than just being a universal constant like Avogadro's number or the conversion from feet to inches. Another example you might see in chemistry might be molar mass, which is specific to a molecule or element. So this workshop isn't about significant figures, and I'm not going to cover them in much detail. And from the sounds of it, everyone will have already, sounds like a lot of you may have already learned about this, but just a quick summary. In this workshop, we're only going to be using multiplication and division. And when multiplying and dividing numbers, your final number of significant figures will be equal to the smallest number of significant figures that you use. For example, the conversion factor 1.609 kilometers to 1 mile isn't an exact value. It's been rounded, so it has 4 significant figures. There are factors such as the conversion from inches to feet or from centimeters to an inch that are exact, and they're considered to have infinite significant figures. And you'll notice it doesn't matter if they have decimals or not. Sometimes like 2.54 in a different context may have 3 significant figures, but for this specific conversion factor, it has an infinite number. And you basically just ignore them when you're figuring out how many significant figures the answer has. Right. Does anyone have any questions before we go into the first example? Right. So our first example, we're going to use imperial units to metric units. And let's say that Omar is traveling overseas and he's driving on an expressway at 85 miles per hour. The speed limit on the road he's traveling on is 140 kilometers per hour. Omar wants to know if he's speeding or not. So what do you guys think should be the first thing we would do when solving this problem? Yep. So we've got to convert miles because miles is the number that we're starting with. And we need to convert it into kilometers since that's the final unit. So how we would set this up is we take our number that we're starting with, and we need to multiply by the conversion factor to go from miles to kilometers. So what is the conversion factor for miles to kilometers? Right? Yep. So I'm going to put right, and then just a quick verification. Does this look like we're good, or do we need more, or do we need to flip the factor around or anything like that? Right. Right. So if everything is set up and ready to go, what will our final answer be? Yep. And in this case, we have three significant figures since our starting number and our conversion factor both have three significant figures. So we're good there as well. Yep. And you pretty much always use the same process for these types of problems. You do since it's a rounded number. In this case, it didn't matter too much because it had the same number of significant figures as the starting value. But if we'd had a value that was a little more exact, like 85.04, then we would have still only had three significant figures because 1.61 only has three significant figures. So if we would have picked 1.6, then the final answer would have had two significant figures. So I'll write that out. Times 1.6. And so in this case, the multiplication would be basically the same, 85 times 1.6. But this time, we have three significant figures in our starting number and two significant figures in our conversion factor. The smallest of those is 2, so our answer is when I have two significant figures. And since the number was rounded down, it turns out to be, it would be 136, but we have to round to two significant figures, and so we round to 140. Yes, I am recording it, and it should be available. I don't know exactly where it's going to go. My assumption is probably going to be the libguides. But yes, it is being recorded, and it will be made available later. All right. So, yep. So as you saw, the basic process was to identify what you start with. Then you need to identify what you're trying to obtain. And then you need to identify your conversion factor, or factors, but this one only had one. And then you'd set up multiplication like I did, although in this one I hadn't used the per hour. So in this case, it didn't matter because the per hour was the same, but watch out for that one. So you'd multiply, the miles would cancel, and you'd be left here with your 137 kilometers per hour. And now that we know what his speed is in kilometers per hour, it's easy to compare it with the speed limit and see that he is, in fact, not speeding. So before we move on to sort of example 1.5, does anyone else have any questions about this problem or not? Right. So this one we're going to do is we're going to see, so this one we did kilometers per hour. Now let's try meters per second. So we want to see how fast he's going in meters per second. Yep. Yep. So what we want to do now is since we have several conversion factors, now we need all of those, right? So we need miles to kilometers, which we know. So I'm going to use this 1.609 from the previous slides. And then we want to go from kilometers to meters. And so what is the conversion factor from kilometers to meters? Yep. What about from hours to seconds? Yep, there's 3,600 seconds in 1 hour. Right, so now that we have our conversion factors, I'm going to start with the starting number, which is 85 miles per hour. This time, we have to be careful to put both units up there, because the previous one, since the per hour didn't change, it didn't matter too much. But this time, it's important, because both of them are going to be changing. And then what's the first thing we should multiply by? Yep. So we'll put the 1.609 up there. Yep. And then what's the next one? Yep. And we only have one unit conversion left, right? Yep, which is the same as multiplying by 1 hour over 3,600 seconds. Yep. The main reason that I'm keeping it in this particular structure is in some more complicated problems, it can help keep track of what units are going where and which ones need to cancel. And indeed, if we go and start canceling them, all the ones that we need to cancel get canceled. And so what do we get as the final value? Yep, 38 meters per second. You're fine. So does anyone else have any questions before I move on to the next slide? Right. So, so, so one of the big things is also that you can do the unit conversion factors in different orders, right? If I flip the orders around, or in this case, I'm going directly to meters, for example, you'll still get the same answer as long as the units are all valid. So, so in this particular one, I use 2 conversion factors instead of the 3 that you used, and it's also possible to use 4. So if you know some unit conversions that you need but not others, sometimes it's possible to recreate the ones that you need using the ones that you know. For example, you may not knowing that there's 3,600 seconds in an hour might be a little harder to remember than that there's 60 seconds in a minute and 60 minutes in an hour, and just using the two separately, like so, for example, especially on a test where you're on a time limit and whatnot. So now, no one has any questions. We'll go on to a slightly more complicated example. So let's do this one. So Maria wants to visit her parents by driving to their house. If it's an 832-mile trip one way, and her car gets 28 miles to the gallon, and it holds 10 gallons of gas in the tank, how many times will she have to fill her tank up when driving there and back? All right. So one time per 832 miles times 20 miles to the gallon times 10 gallons. So so the trip is 832 miles, right? Yep, times 2. Yep. Hmm. Here's the here's the 832 is in the denominator, though. So can you see what went wrong when setting this up? What happened? Well, that's what yeah. So that's what the math is. That's what it's supposed to be at the end, right? So so in so what we have to do is we have to flip everything over, right? Right. So this top one is a good example of what happens when all your conversion factors are in the or are flipped upside down, right? That's why having them in the correct way up is important. Otherwise, in this case, you're going to get probably you're going to get a different answer than you were expecting, and the units aren't going to make any sense. Which is a good way, if you're doing this, to see if the original attempt may have been erroneous. Is if your units come out strange, it's a sign that something may have gone wrong. In this case, times per tank isn't a very useful unit, and it's definitely not going to help us with the problem in this case. Yep. So sometimes the values that you get in the problem, because you'll notice in this answer, the one where all the units are lining up correctly, a lot of the conversion factors look upside down. Like I said, all conversion factors are reversible. So depending on what you need, you can always flip them to be their opposite. Even for things like miles per gallon, you wouldn't normally reverse them because gallons per mile isn't a you almost never hear a unit like that. But in this case, you want to set it up as gallons per mile so that your miles can cancel out. And so what you would yep 6 times. And so if you just did these two, what you would get is how many gallons that you would need. Um, welcome, Pamela King, who just joined. If you could please state your professor and your course for in the chat. We're currently in the middle of the presentation, but it is being recorded and will be available later for those parts that you missed. Right. Right, so in this case, so first we would so the way that you solved it is slightly different than the way that the way that I had set it up. I had multiplied the distance by 2 before setting it up, but the way that you did it here, where the number of times was listed as separately, it's perfectly valid. Like I said, there's more than one way to set these up. And so we start at, in this case, either 832 or 1664. We end at the number of times she fills her tank up. And then we go ahead and we find our conversion factors, both of which are stated in the problem. And then we set up our conversions, cancel our units, do our multiplications, and we get 6 tanks of gasoline. So another slightly different question. So the question here, if she had started with a full tank of gas, how many times will she have to fill her tank up? Yep, because one of the fill ups she doesn't have to do since she already had a gallon of gas. So our next problem is a chemistry problem. So we're given a chemical equation for the combustion of propane. If we had combusted 5 kilograms of if carbon dioxide was produced from the combustion, how many kilograms of propane were there when we started? Yep. So if you would convert kilograms to grams, then grams to moles, then moles to moles, and then moles to grams, and then grams to kilograms. I'm going to write, so I'm going to go ahead and write those conversions. So some of those aren't going to be, you'd have to look them up in your periodic table. So I'm going, since we're a little bit, since we started a little bit late, I'm going to go ahead and write the conversion factors up on here, at least for the atomic rates. And then from the chemical formula would give us the conversion factor to go from moles of CO2 to moles of propane. And then the conversion factor from grams to kilograms, since it's a metric unit, will be 1,000 grams to 1 kilogram. Right. So if we set this up as a unit conversion problem, we'd start with our 5 kilograms. And then what will be the what would be the first conversion factor? But like, so what order would you put the conversion factors in? Right. That's one. Right. After we convert kilograms to grams, we can now convert from grams to moles, right? And we can convert to moles. And once we have it in moles of propane, we then just do the reverse, right? right? So notice each one is lined up as a ratio multiplied together, right? And now that we have it all lined up, we can start canceling units. And so when all is said and done, what do we get for our final answer? Did you also get 1.84? Okay. Does anyone have any questions before we move on? All right. So we got 1.84 kilograms of C3H8. So this is one of the reasons that dimensional analysis is this particular technique for doing so can be very helpful, is everything is set up kind of in a row. Everything is in order, and you can just systematically cancel units, multiply, and divide. Because there's 1, 2, 3, 4, 5 unit conversions in this problem. So another thing that you can do is that unit conversions can be raised to powers. The ones you most commonly see will be squares and cubes, second and third powers. So whenever you need to raise a unit to a second or third power, both the quantity and the unit in the conversion factor will be raised to the same power. An example, the normal conversion factor is 1,000 meters in a kilometer, but there will be the square of 1,000 meters in the square kilometer, which would come out to be 1,000,000 square meters, because that's 1,000 squared. So 1,000,000 square meters in a square kilometer. Similarly, if you cube 1,000, for example, a cubic unit, you'll get 1,000 cubed meter cubed, 1,000 cubed cubic meters in 1 cubic kilometer, which turns out to be 1,000,000,000 cubic meters. So some quantities that measure the types of things that squared and cubed units don't necessarily have powers. For example, area would be squared lengths, like square meters, but a common unit that also measures it is an acre. For example, there are about 43,560 square feet in a single acre. Similarly, volume can be measured in units of cubed length, such as meters cubed, but your common unit used for volume is the liter. There are 1,000 cubic centimeters in 1 liter. The value is given directly as a squared or cubed unit, like above for the acre and the liter. There are no need to square or cube any of the units because it's already been done. But if you're deriving a unit from the original base unit, then that's when you'll need to square or cube your values. Does anyone have any questions before we continue? Not necessarily. It depends on Depends on the particular class and the problem. Like a lot of times you'll have references, like either it'll be like a common conversion factor might be 12 inches to 1 foot. Those you may need to memorize, but for a lot of times you'll be given a reference sheet or the problem will state the conversion factors that you'll use. In a homework problem, it might be expected that you need to go into the chapter of the book in order to look for like a table of values. Or, for example, a common thing in chemistry is you'll look up, you're given a periodic table, and then you have to derive from the periodic table the conversion factors. Like in the previous example, I already did the math to find the 44.01 and the 44.08. But if you're like on a test, you'd be given a periodic table and you would end up doing that yourself if it isn't given explicitly in the problem. So so like I said, it would depend on the class, it would depend on the problem, and it would depend on the specific circumstances. Did that answer your question? No problem. Right, so here's an example of squared or cubed units. Say a family buys a rectangular plot of land 1,000 feet long and 500 feet wide, or 500,000 square feet. How many acres of land is it? How many acres of land would this be? And since we're low on time, we won't worry too much about the square miles. We'll just worry about the acres. Or rather, if you want to, you can work these problems a little bit later, since I think this session will be closing in a few minutes. So did you want to go through this example, or do you think you understand squared and cube units well enough without an example? All right. And so our last topic for this session is going to be the qualitative approach to this. So the technique we were using before is the quantitative technique where we're working with the numbers. But the qualitative technique is essentially the same idea. It's just that instead of using numbers, we're just using only the units. And then we would look and see what the units come out to. And if the units aren't coming out to what they should be for to solve the problem, you can then change around how you are ordering your conversion factors. It's so that before you do any of the math and get a numbers. And sometimes we have to, like in that chemistry example with 5 conversion factors, that's a lot of input in the calculator or hand calculations, and you can save quite a bit of time sometimes by only using the units, checking that they're in the right order, and then doing the numbers afterwards. It can also, if you're having trouble remembering a constant, you can also this can also help see if it is in fact the correct units, because if the units are incorrect, then it would come out strange at the end, and you may need to look up that particular constant. So if we were to do an example like this, since it's qualitative, we don't necessarily need to actually start with the numbers, right? We can derive our conversion factors, but we just plug in the units, right? And then if the units come out strange, we don't have to worry about actually doing the math until we get the units in the correct order. Yep. So that would be the correct orientation for all your conversion factors, because when you cancel everything, you're going to be left with just money. And of course, if you had put the units in the wrong order, you might get something like this example up here where nothing cancels. You get the strange miles squared per times dollars O per gallon squared. Whenever you get a unit like that that makes no sense, that's almost always a sign of that something has gone wrong. And you may then you would want to look over it just to see if you can spot where the error happened. So to summarize, dimensional analysis is a very fundamental foundational technique to handle unit conversion problems. They're used throughout the sciences, they're used in medicine and in other places. And it's a common place you might find dimensional analysis problems in medicine, such as in nursing, would be dosage calculations. There are other places where dimensional analysis can be used to solve, such as like in the culinary arts, you may need to convert between milliliters and teaspoons, and you could use the exact same techniques to do that conversion. And you can use this technique both quantitatively to solve for a numerical answer, or qualitatively to see what units or type of unit that you would get at the end. Right. Does anyone have any questions or comments about this workshop? At this point. No problem. Yeah, there's all kinds of little details in this type of stuff that can pop out, and especially in classes where it's important for significant figures, you can end up getting points off without even really knowing why or what you did wrong. So uh, I'm glad you enjoyed it. And does anyone else have any other questions or comments, or is everyone good at this point? Hey, no problem. And then if so, before we let let her finish typing before I continue. No problem. Hey, if everyone could do so, if you would like to leave your student contact information, either in the chat or in a PM for the sign-in sheet, I'll go ahead and add that. And once that's done, we will be done here. All right, awesome. Right, let me you go ahead and switch to the poster, which contains all this particular poster will have all of the sessions. For example, it has so the next one is going to be the Math for Science students. It'll be hosted by David Prinzhorn. It'll be Friday, September 11th. It's 1 to 2 p.m. And then if you want all the other, like for example, the dosage measurements one is coming on September 12th. So if you want, you can take a screenshot or write this down. This poster has all of the workshops we're going to be doing this semester. I thank you. You have a wonderful day as well.
You are currently the only person in this conference.